Hello. I hope you can hear me well. And we will start. So today we're talking about complex numbers. So I'll take it easy at first, and at the end we'll do some more challenging questions. But of course, I've done a couple of webinars on complex numbers before, so you're welcome to watch them on our YouTube channel. Otherwise, let's go. Oh, by the way, just a quick question in the chat. Um, can you please vote if you are new to Compos or are you old? Are you returning? So just put in new or old student. Just let me know. Old, old, old. Okay. All right. So okay. Excellent. Basically, no new students today. That's so you know what Compos is about. So I don't need to tell you about Compos. Okay, so you should see my screen. And I'm starting quite easy, so I've done more complex, more complicated, complex numbers in the previous webinars. So you're welcome to watch last year's webinars and the year before. Today, this one. On the Argand diagram below, the point A represents the complex number 4i, so that's 4i, and point B represents the complex number minus 5 plus I. The shape below is a square. So determine the complex number represented by the point C. Well, this is a geometric problem, right? So it's not really about complex numbers. It's more like geometry. So basically, the question is find the coordinates of point C. Oh, well, what can we do? Well, we can say that interesting. Well, yeah, you can you can take different approaches here. Let's find the gradient of AB first, or rather vector BA. Okay, BA is a vector. I'm going to use vectors today, so it's going to be, so A is 0, 4, and B is minus 5, 1. So BA is 5, comma 3. Now BC is a perpendicular vector with the same well, it's a rotation. It's a 90-degree rotation. So BC, well, first of all, is perpendicular, and it has the same. It's perpendicular, and it has the same magnitude. So BA is 5, 3. What do you think BC is? Like, on an intuitive level, can you tell me the coordinates of vector BC? Or what is the column vector corresponding to BC? 3 minus 5. That is correct. 3 minus 5. Minus 5. Of course. So it has to have the same magnitude. And it kind of has the opposite gradient because the gradient is going to be if it's 5/3 in the 3/5 for this one, the gradient of BA, the gradient of BC is going to be minus 5/3, which makes perfect sense. And then if you want to find point C, so vector OC, OC can be written as OB plus BC, just using the rules for vectors. So OB is minus 5, 1, plus BC, which is 3 minus 5, which gives you minus 2 minus 4. So C is minus 2 minus 4. And if you want to find OD, OD can be written as OC plus CD. And we know that CD is the same as BA. So OC is minus 2 minus 4 plus CD, which is 3 minus, 5, 3. This gives you minus 2 plus 5, that's 3. Minus 4 plus 3 is minus 1. So that's 3 minus 1. So as I said, not really a complex number question. It's more like a vector problem. But there are other ways you can do this. You could do this using coordinate geometry. I wonder if you could use it just using complex numbers. I'm not sure. Well, I mean, you can certainly, but yeah. Okay, problem 2. Give the equation, give your answer in Cartesian form. So I want to do this equation in 2 different ways. So the first is algebraic. Well, you just write it down as z cubed minus 1 equals 0. And you know that 1 is a solution. Z equals 1 is a solution. So now you can divide by z minus 1. Now I'm going to write this out as z cubed plus 0z squared plus 0z minus 1. So I'm using long division to divide z cubed minus 1 by z minus 1. And that gives me z minus 1 is z squared. Z squared times that is z cubed minus z squared. This is going to be z squared plus 0z. Z squared divided by z, that's plus z. Z squared minus 1z. That's z minus 1. Z minus 1, so that's plus 1. Z minus 1 and 0 remainder. Therefore, you can write z cubed minus 1 as z minus 1 multiplied by z squared plus z plus 1. And that's equal to 0. And that means that z is equal to 1, duh, or, that's the first solution, or z squared plus z plus 1 equals 0. Here, there's different ways I can do it. I will use the completion of the square. So z squared plus z plus a quarter minus 5 quarters. No, that doesn't make any sense. Plus 3 quarters equals 0. Z plus a half equals minus 3 quarters. So z plus a half is plus or minus root 3 over 2i. So z is equal minus a half plus minus root 3 over 2i. So that's z 2 and 3. So I have 3 solutions. How well do you understand how I got the solutions on a scale of 0 to 10, please? Okay, so everyone understands that. And lovely. So the answer is z1 equals 1, z2 equals -1/2 plus √3 over 2i, and z3 is going to be -1/2 minus √3 over 2i. Lovely. Now, I'm going to use a different method now, doing the same thing. I'm going to use the exponential form. So using exponential form. I fell in love with this method when I first saw it, and I hope that you will too. Z cubed equals 1. So what I need to do is I'm going to write 1 in modulus argument form. So 1 is e to the power 0. 0 I0. That's not satisfying enough. I need all the possible values. So it's going to be plus 2 pi I. So I 2 pi r 2 pi k. Do you understand what I did? I 2 pi k. On a scale of 0 to 10, do you understand what I did? Ooh. Gave some 10s. 2 pi k. Okay. For any k, this, for any k integer k, this is going to equal to 1. Let's check. Suppose k equals 0. Well, yes, e to the power 0 is 1. If k is 1, then I have e to the power I 2 pi. So that means it is a complex number with argument 2 pi, which is this number. Here, that's argument is 2 pi. So the modulus is 1, and the argument is 2 pi. And 2 pi is this number. If k is 2, it's going to be e to the power I 4 pi, which also means r equals 1, argument is 2 pi. So it's the same point, 1. So whatever k I choose is going to be 1. So I said that 1 is all of these numbers are equal to 1. So I've written down all the possibilities how you can make 1 on the complex plane. So you rewrite this. Z cubed is equal to e to the power I 2 pi k. And now you put both numbers to the power 1/3. And you get z is equal to e to the power I 2 pi k over 3. Okay? And there are 3 possibilities. For k equals 0, z 1 is equal to e to the power 0, which is 1. For k equals 1, z2 is going to be e to the power I 2 pi over 3, which is 1 multiplied by cos 2 pi over 3 minus I sine 2 pi over 3. Oh, sorry, plus, of course, which is cos 2 pi over 3, that's minus 1/2, and sine pi over 3, that's √3 over 2i. And for k equals 2, z is the third option, is e to the power I 4 pi over 3, which is cos 4 pi over 3 plus I sine 4 pi over 3, which is minus a half minus root 3 over 2i. So this method is actually much shorter than this, than dividing, than doing long division. All you need to do is write the right-hand side number in the exponential form, and then take everything to the power, and then you just write out the three answers. Let's do another example. Let's z to the power 5 is equal to 32. Okay, easy one. So what do you want? You want to write 32 as, no, actually no, let's make it more complicated. Let's make it 32i. All right, it's 32i. So that will make it more interesting. 32i. So I need to write 32i as a complex number. So it's going to be 32, sorry, as a exponential form, I to the power I pi over 2 plus 2 pi k, where k is any whole number. Okay, 32i is the same as this because it has an argument of pi over 2 plus 2 pi k. Yeah, because it could be 90, but it also could be 450. And then you just take it to the power. So z is equal to 2 because, well, okay, I'll write it 32 to the power 1/5 multiplied by I pi over 10 plus pi k over 5, 2 pi k over 5. Yeah, that's it. And then you just list the values. K equals 0, 1, 2, 3, 4. And that gives you the 4 possibilities. So Z1 is 2 e to the power I pi over 10. Z2 is 2 e to the power I pi over 10 plus 2 pi over k. That's going to be 4 pi, 5 pi. What? 4 pi, 5 pi over 10. Okay, I'll change that. 4 pi over 10. Yeah, that's 5 pi over 10. Z3 is 2 multiplied by I 9 pi over 10. Z4 is 2 I 13 pi over 10. Z5 is 2 I 17 pi over 10. So these are the 5 possibilities. Does that make sense? Do you think you understand on a scale of 0 to 10? Do you think you understand this method? Have you, or maybe you've done this method before? Which is 2 cos pi over 10 minus I 2 sine pi over 10, which you can, of course, write it out. Lovely. They are roots of unity, I mean, after all. Okay, problem 3 is sort of randomly placed here, but anyways, consider the complex number z is W1 over W2, So all we need to just, well, what z is w1, which is root 2 plus 6 root 6I over plus root 3I. Multiply this by 3 minus root 3I, root 3I. So similar to 9 plus 3, similar to rationalizing the denominator. And this is going to be 3 root 2 minus root 6I plus 3 root 6I minus 3 root 2 I squared. Okay, so that's going to be 3 root 2, that's going to be 6 root 2 minus 2 root 6 plus 2 root 6I divided by 12. It's going to be root 2 over 2 plus root 6 over 6I. Oh, they didn't ask for that. Sorry. We need to write them in modulus argument form. So we can write it as modulus W1 is 2 plus 6, which is 8, and W2 is 9 plus 3, which is 12, and argument W1 is root 6 over root 2. That is arctan root 6 over root 2, which is arctan root 3, which is pi over 3. And argument W2 is root 3 over 3, arctan over 3, which is pi over 6. Okay, so if you are z is the modulus of z. The modulus of z is going to be modulus of w1 divided by modulus of w2, which is 8 over 12, which is 2/3. The argument of z is argument of w1 minus argument w2. That's the rule. If you divide numbers, you subtract the arguments, and that is argument 1, which is pi over 3, minus pi over 6, which is pi over 6. Find the smallest positive integer value of n so that z to the power n is a real number. So A, B. Z to the power n is a real number. N is question mark. Well, and it's a 2-mark question, so it's not supposed to be very difficult. What do you think we need? What do you think we need for that question? So this is z, and we know that z to the power n. Well, what happens to the argument? What happens to the argument when you argument z to the power n is n multiplied by argument z. Do you agree with that? And if z to the power n is real, that means that the argument zn is either 2 pi k or argument z to the power n is pi plus 2 pi k. These two can actually be combined. How do you combine these two into one? Do you know? Pi k, yes. Argument zn is pi k. So if the argument is a multiple of pi, that means it is a real number. But we already know that argument z is pi over 6. So it's going to be n multiplied by pi over 6. And this is k pi k. So pi k is equal to n pi over 6. So k is an arbitrary number. So with the smallest power would be 6. Oh, the modulus, yes, is... Yes, sure, sorry. Yes, so that would be square root of 2/3. But that's still doesn't make any difference here. So n has to be 6. N equals 6. The smallest value is 6 because we know the argument of z is pi over 6. If you take it to the power 6, it would be 0. It could also be 0, but it says smallest positive integer. Otherwise, it would be too easy. Z to the power 0 would be a real number. Okay. Z to the power 0 is 1. Does that mean that I to the power 0 is 1? Is I to the power 0 1? Yeah, it must be. Must be, of course. Because I is 1 e to the power I pi over 2. And if you take it to the power 0, that's going to be 1 to the power 0 and e to the power 0, which is 1, of course. Lovely. Problem 4. Consider the complex numbers z1. So if you haven't seen this notation, that means cosine I sine. So this simply means 3 cos 120 plus I sine 120. I actually added this question just to use this notation. The question is not particularly interesting. Okay, so what do we know about z1? So we know that the modulus is 3 and the argument is 120. Here it's 2 plus 2i, so the modulus is 2 root 2 and argument is 45 degrees. So if you're doing z1 over z2, z1 over z2 is going to be 3 over 2 root 2 multiplied by e to the power I 120 minus 40. 120 minus 45, which is 3, 2 root 2 e to the power I 75 degrees, which is 3 root 2 over 4 cos 75 plus I sine 75. In Cartesian form, well, you just need to cos 75. 75 minus apologize, just a second, give me a minute. Well, I mean, do we want to calculate cos 75 here? Cartesian form. So this is the modulus argument form, of course. Cartesian form. Let me just check. Oh. Yeah, you just of course you can do just the Cartesian form rather than calculate cos 75 and sine 75. Yeah, you could just divide them. So you can write this out as 3 cos 120 is minus a half plus I sine 120, so I root 3 over 2. And then Cartesian, we're still doing question A. That would be 3 minus 3 over 2 plus 3 root 3 over 2I over 2 plus 2I. You multiply it by 2 minus 2I, 2 minus 2I, which gives you 4 plus 4, 8. And that would be minus 3 plus 3I plus 3 root 3I plus 3 root 3, which would give us minus 3 plus 3 root 3 over 8 plus 3 plus 3 root 3 over 8I. Cool. Yeah, that's exactly what it is. Now, if you equate them, if you make them equal to each other, this part and this part, you can write 3 root 2, so this is part B, 3 root 2 over 4 cos 75 plus I 3 root 2 over 4 sine 75 equal to minus 3 plus 3 root 3 over 8 plus 3 plus 3 root 3 over 8i. Now, this is a complex number, this is a complex number. That means that the real parts have to equal to each other, and the imaginary parts also have to be equal to each other. And here we just write 3 root 2 over 4 cos 75 has to equal minus 3 plus 3 root 3 over 8. 2 and 3 divided by 3, so 1, 1, and divided by root 2. So cos 75, oh, we actually didn't need cos 75, but that's fine. Just in case, it's going to be minus 1 plus root 3 divided by 2 root 2. Interesting result. That was the question. Oh yeah, and that is, thank you. That is sine 15. Thank you. That makes perfect sense. We can use that, and then we can do sine. So 3 root 2 over 4 sine 75 equals 3 plus 3 root 3 over 8. And that means, in a similar fashion, this is 2 divided by 3. That's 1, 1. Sine 75 is 1 plus root 3 over 2 root 2. Okay, and then we just multiply it out. So sine 15 multiplied by sine 45 multiplied by sine 75, which gives us minus 1 plus root 3 over 2 root 2 multiplied by root 2 over 2 multiplied by 1 plus root 3 over 2 root 2. And that gives you, that cancels, that's 8. And that's going to be 3 minus 1, which is a 8 root 2, 1 over 4 root 2, which is root 2 over 8. Good. There's a different way you can do sine 15 or sine 45. If you want to do sine 15, all you need to do is sine 45 minus 30, and that would be sine 45 cos 30 minus sine 30 cos 45. And sine 75 could be done as sine 45 plus 30, which would give a similar result. Okay. I to the power 4 divided by I to the power 4 is 1 divided by 1. Yes, thank you. That is okay. Problem 5. For complex numbers Z1 and Z2, interpret geometrically that Z1 plus Z2 is always less than or equal to Z1 plus Z2. Does anyone know what this is about? This is a well-known inequality. Do you know what it is? The triangle. Yeah, it's a triangle inequality. Okay. The triangle inequality. So if we have two numbers, let's say Z1 and Z2. So this vector represents the vector Z1. This represents the vector Z2. And the vector Z1 plus Z2, that's Z1 plus Z2. Z2. So basically we can redraw this as Z1, Z2, and this is Z1 plus Z2. Actually, if we want the length, it's modulo Z1, modulo Z2, modulo Z1 plus Z2. And of course, in any triangle, the sum of two sides, so modulo Z1 plus modulo Z2, is always less than or equal to Z1 plus Z2. It's the triangle inequality. If the vectors are collinear, then we have an inequality. Let's say with vectors Z1 and vector Z2, then this vector is Z1 plus Z2. And then in this case, Z1 plus Z2. So if Z1 is collinear with Z2, not just collinear, but also in the same direction, then that's equal. They're equal. Z1 plus Z2. Okay, hope that makes sense. So quite a reasonably easy question. Okay, we're getting to interesting stuff. Loci on Argand diagrams. Sketch the following subsets of the complex plane using Argand diagrams. Give reasons for your answers. So the real part of 1 plus I multiplied by Z is greater or equal 0. So how do we even approach that? So the real part of 1 plus I multiplied by Z is greater or equal to 0. Well, there are several ways of doing it. Well, first you can recognize what this is. Honestly, I can't recognize what this is. So you just need to write Z as right in a Cartesian form. So remember that Z is X plus IY, where X and Y are real numbers. So this will be real part of 1 plus I multiplied by X plus IY greater or equal to 0. So the real part of X plus IY plus IX minus Y is greater or equal to 0. But the real part of that is just X minus Y. So that's X minus Y greater or equal to 0. And it's actually Y greater or equal X. So it's all the values where Y is greater or equal X. So this is X, this is Y. So it's this part. This is the shaded region. This line is Y equals X. All right. Can I vote? Can I get a vote on a scale of 0 to 10, please? 10 being I understand fully what's going on. It is. Apologies. It's the other way around. So it's the other part. Right. Okay. So what I did, I just replaced z with x plus iy and unwrapped it. Let's do the second one, ii. So we have two inequalities. We have modulus of z squared is less than or equal to 2. And we have the real part of z squared is greater or equal 0. How does that even even? Well, it's the same idea. We write down x plus iy squared modulus is less than or equal to 2. Okay, modulus x squared minus y squared plus I 2xy less than or equal to 2. Now the modulus of a complex number is the real part squared. So modulus of a complex number is the real part squared plus imaginary squared square root. So it's the square root of x squared plus y squared to the power 2 plus 2xy squared. That's a minus, sorry. Less than or equal to 2. So I continue. That's x to the power 4 minus 2 x squared y squared plus y to the power 4 plus 4 x squared y squared less than or equal to 2. I can see that this just turns this goes and this turns into a plus. Now we have this, but this is x squared plus y squared to the power 2 less than or equal to 2. Now, because this cannot be a negative number, x squared plus y squared is a positive number, I can get rid of the square root. So x squared plus y squared is less than or equal to 2. And this is a circle with radius square root of 2 at 0, 0. Interesting. Next bit is this. So this is going to be the real part of that. So we've already established that x squared, z squared is this. So it's the real part of this bit, x squared minus y squared, plus I 2xy, and that's greater or equal 0. But the real part of that, it just excludes this bit. So it's x squared minus y squared greater or equal 0. Okay. There are different ways you can do this. One of the ways is this, modulus x squared is greater or equal y squared. And this is equivalent to saying modulus x is greater or equal modulus y. And here you can say modulus y is less than or equal modulus x. So y is less than modulus x, but greater than minus modulus x. So you can draw these two lines and say, okay, y is less than modulus x, so this is modulus x. So we're below modulus x. Now y is greater than minus modulus x, and minus modulus x is like this. So it has to be between these two lines. So it has to be here and here. Or you can do it like this. X minus y, x plus y, less than, greater or equal 0. That means x minus y greater 0 and x plus y greater than 0, or x minus y less than 0 and x plus y less than 0. That means y is greater or equal x and y is greater or equal minus x. Doesn't make any sense. Y is less than or equal x, y is greater than minus x, or y is greater or equal x, y is less than or equal minus x. That's more complicated. I mean, I wouldn't go there. It's the same. Okay. Lovely. You could. So that's y. That's y equals x. This is y equals minus x. Either y is less than x and greater than minus x, so it's like this, or it's greater than x and less than minus x, so it's like this. So same thing. So basically, now the answer. You're inside the circle, and you are in these what do you want to call them? It's a circle, and you're inside these lines. So it's this. It's this subset of complex numbers on the complex plane. Finally, number I. I'm just going to modify it slightly. I'm just going to make this into a 3 because I really didn't like the way it turned out here. Now, this is the easiest one, and it's not. So what do we know about Z1 and Z2? Well, we know that Z1 has a modulus of 3, and Z2 has a modulus of 1. So Z1, modulus of 3, 1, 2, 3. So it's a circle of radius 3. 2, 3, 1, 2, 3. So Z1 is somewhere here. Z2 is this one. Z2. But the thing is that these two are independent. So Z1 could be anywhere, any vector which starts at the origin and ends at the circle. And Z2 could also be any vector. So for every value of Z1, we have infinitely many values of Z2. Let's say for simplicity, there's 360 possibilities. Let's say we can only allow to do whole number of degrees. So for every argument of Z1, there are 360 possibilities. So let's say Z1, suppose argument of Z1 is 30 degrees. That means it goes like this, Z1. Now Z2 can be anything. So Z1 plus Z2 is a circle. Z1 plus Z2 is a circle around this point. But then Z1 moves. Z1 moves, and it's another circle. Z1 moves, and it's another circle. Do you see how this is? So you have Z1 and Z2. And this is Z1 plus Z2 plus Z2. Assuming that Z1 is fixed, Z2 can make a whole circle, right? Z2 can go around this point. So what am I getting at? I'm saying that the shape described by this equation or these equations is this. So it's a circle of radius 1, circle of radius, oh no, we need circle of radius 3, circle 1, 2, 3, 1, 2, 3, 1, 2, 3. And on top of that, at every point of that circle, we have a circle of radius 1. So that's that. So that makes actually a circle of radius 4, and circle of radius 2, and all the points in between. You can have all the points in between. So Z, this is equivalent to saying modulus Z is less than 4 and greater or equal to, which is quite cool if you think about it. It's like a double pendulum, you know. You have one arm of a pendulum and a small pendulum at the end, and they go all sort of squiggly lines. Yeah, so it's a pendulum on another pendulum. So it's like Z1 is a pendulum, and at the end of Z1 there's another pendulum, Z2, and Z2 can move in any way you like. It's just the length of that pendulum is 1. So basically, yeah, that's I think it's quite cool. Anyways, this one, number 7, is the last one for today. Prove that the equations this and this describe the same locus in the Z plane. Sketch this locus. Okay, so let's see. I'm going to use the same. Well, actually, I don't need to use the same because I already know. I take the square root of that, and I do modulus Z minus 1 plus I equals square root of 2. Because both sides are positive, I can take the square root. I'm allowed to do that. And that means, and both sides are real, so I don't have to worry about complex numbers, right? I'm taking the square root of a real number. It's a circle. It's a circle. Center 1 plus I, and radius square root of 2. So let's draw this circle. X, I, Y. This is 1. This is I. This is 1 plus I. And square root of 2. Oh, it turns out it goes through this. It goes through the origin. So it's slightly more than 1. It's 1.4. 1.4. And it goes like this. So this is the locus of points described by this equation. Second, let's call it A. Now B. Modulus Z minus 1 minus I squared equals 2 modulus Z minus 1 squared. How do you even do that? Well, I think the easiest way is doing the same thing. Z equals X plus IY. So you substitute that in. X plus IY minus 1 plus I squared equals 2, and X plus IY minus 1 squared. That is X minus 1. So the real part of this is X minus 1. X minus 1 squared plus Y plus 1 squared equals 2 multiplied by X minus 1 squared plus 2Y squared. So I'm just using the moduli. Okay, so open the brackets. So x squared plus 2 minus 2x plus 1 plus y squared plus 2y plus 1 equals 2x squared minus 4x plus 2 plus 2y squared. 2 goes away. 2 goes away. I have x squared minus 2x. Oh, 1 and 2 go away. Plus y squared minus 2y equals 0. This is unsurprising. It shouldn't be surprising because if x is 0 and y is 0, it's true because it actually goes through 0.00. So I'm on the right track. X minus 2x plus 1, x squared minus 2x plus 1. I'm completing the square plus y squared minus 2y plus 1. And of course, I need a minus 2 equals 0. X minus 1 squared plus y minus 1 squared equals 2. And this is a circle, center 1, 1, radius square root of 2, which is exactly the same. So I've just proven that these two equations describe the same circle. And of course, if you think about it, because this is the center, this is 1, so this has to be 2, right? Without any doubt, because this is 1. From symmetry, this has to be 2. Okay. Now, if I do the last one. Now, there might be a more beautiful way of doing it, but I had limited time to come up with a solution. So I did it the following way. So you need to show that this equation is also, or describes part of that. So I'm going to use the fact that the argument of the division, the argument of a dividend divided quotient. The argument of a quotient is the difference in the arguments. So I'm going to rewrite it as argument z minus 2 minus argument z equals to pi over 4. And what is z and argument z minus 2? Well, you can draw it and say argument z. So let's say we have a point z, which is here. Z. Argument z, that's that. This is argument z. And argument z minus 2 is the similar thing, but drawn from 2. This is 0, 1, 2. This is argument z minus 2. It's certainly a different one. Let's label them. Let's say that this is alpha and this is beta, just for convenience. So this is 0, this is 2, this is beta, this is alpha. Now this is going to be pi minus beta. Oh, sorry. Before we do that, let's write this out. So this is beta minus alpha equals pi over 4. Beta. So this is going to be pi minus beta. And this is going to be pi minus alpha minus pi minus beta. Just using the triangles, which can be simplified as pi minus alpha minus pi plus beta, which is beta minus alpha, which is, ta-da, pi over 4. Interesting. So I've shown that this line means that that z is such a point that it forms a triangle with angle pi over 4. Okay. Now, if you have 2 points and you draw all possible points such that this is pi over 4, what do you get? If you find all the possible points, it is a circle, indeed. Oh, it's part of a circle. It's part of a circle. Right? It's a circle theorem. Angles subtended by the same arc. Angles in the same segment are equal. Okay. So it's a circle. And to find the radius of that circle, well, we know that this is pi over 4. So the central angle would be pi over 2. So this would be pi over 2. And this, if this is 0 and 2, so this is 2, and that means that this is an isosceles triangle. So it's 2. This has to be square root of 2. Is it square root of 2? Yeah, square root of 2, square root of 2. And that means this is 1. So the center of the circle is 1, 1. 1, 1. So we can prove geometrically that the center of the circle is indeed 1, 1. This is quite satisfying. Okay. I really hope this was useful. So type 1 if you've learned something new today. Type 0 if you haven't learned anything new today. Okay, that's good. That's the aim of today. And all right, I'll leave you here. Enjoy completing the assignment and submitting it. Now, if you are a current student, you just need to submit it. We don't look at your score. Okay. Right. All right. See you. Yeah. So there is no webinar next week. I'll just double check. Webinar. Next webinar is. Oh no, there is. Sorry, there is a webinar next week. I'll be doing gravity and orbits next week, and there's no webinar on the 10th. Yeah, but there is a webinar. So see you all next week.